Hello, I'm Siddhant Prakash, and today I'll be talking about our work Blind Augmentation, Calibration-free camera distortion model estimation for real-time mixed reality consistency. This research was done at University College London with my colleagues from Birmingham City University and University of Leeds. Our work deals with modeling camera distortions for mixed reality use cases. Video pass-through mixed reality has picked up pace in the last couple of years with the introduction of devices like the Apple Vision Pro and Meta Quest 3 in the market. One of the salient characteristics of these devices are the cameras. In a typical device, multiple cameras are now being used to get the background video feed for pass-through along with spatial information for localization and tracking. Cameras are ubiquitous in nature, ranging from large DSLRs and mirrorless cameras to much smaller CCTV and mobile phone cameras used in head-mounted displays. No matter which cameras we use, distortions are introduced during the capture process. As can be seen from this image, multiple distortions can be present such as noise due to sensor, motion blur due to dynamic scenes or user movement, and defocus blur due to lens geometry and depth of field. A lot of effort goes into reducing or removing such distortions, but many a times we want to preserve such distortions for aesthetic purposes or visual cues which could be desired by the user. Alas, these camera distortions make the augmentations inconsistent as the virtual content are usually rendered and are free from such effects, making them stand out, as can be seen here. Our key idea is to do self-calibration using the final image captured by the device. We do that blindly without any calibration target placed in the scene. Instead, we use off-the-shelf methods for distortion removal, providing self-calibration targets. We propose a fast optimization scheme which infers the distortion parameters to create a camera distortion model in real time. Using this model, we can resynthesize the distortion over the virtual content which matches with the background distortions present in the image, enhancing photorealism. As can be seen from this frame, we have introduced the right amount of noise, motion blur, and defocus blur over the virtual balls to make it seem like they belong in the scene. Our model is device agnostic too, since all we need is an image from the device to recover the distortion model. This image can be a result of single camera capture or fused multiple camera captures. The capture device is represented in this distortion space without the need for any camera information or known calibration targets placed in the scene. Now let's look at some prior work in this domain. Early works in mixed reality focused on correcting camera distortions or reintroducing them using explicit calibration targets such as checkerboard patterns, printed sheets of grayscale white noise or color charts, etc. Some also required measurement under controlled condition and camera pose information. Our method do not have any such constraint. More recent works use neural networks to model these distortions. We do not use such slow and specialized networks. Our work focuses on introducing sensor noise, motion, and defocus blur, while we leave other distortions for future work. Let's dive a little deeper in how these methods work. As can be seen from the images, Okumura et al. Uses black and white circular markers which has sharp edges around them. If there is camera motion, the markers are blurred and we can infer the spread of the blur from the pixel intensities around the edges, thus recovering the blur radius. The recovered radius is used to synthesize blur over the virtual object as can be seen on the right side of the image. The method works well but requires this specific kind of marker to be placed in the scene. Getting rid of requiring markers in the scene, Mandel et al. Learned the different parts of the camera pipeline as a neural function. Although the data used to train these networks also come by capturing images of calibration targets for the respective parts of the pipeline for which the network is trained. For example, a planar object is used for lens net and a color chart is used for radiometric calibration of sensor net and ISP net. Our optimization is fast and can reflect any change in camera or scene conditions without requiring camera metadata or a pre-calibration step. Now I'll describe our pipeline to create the camera distortion model blindly. In our training step, We infer distortion parameters from a given input frame to represent the camera in the distortion model space. To do that, we run off-the-shelf methods to undistort the images, providing self-calibration targets. Resynthesizing the distortions over the undistorted images requires knowledge of the scene geometry, which can also be inferred using off-the-shelf methods. Once we have these, we can now synthesize the distortions over the undistorted images with varying parameters and compare to the input frame to estimate the correct distortion parameters, thus exploring the distortion space. Once we have inferred the correct distortion parameters, given any other frame in the scene, the virtual composite frame, and the geometry buffers for the virtual frame, which can be obtained from the renderer, we are able to synthesize the distortion with correct parameters on the virtual objects, and then finally composite with the background image, obtaining our final composited frame during deployment. We list the off-the-shelf methods used for all our operations performed in the optimization pipeline in table 1 of our manuscript. The key methods are the state-of-the-art image restoration works, which are used for denoising, demotion blurring, and defocus blurring. For obtaining scene geometry, we use Midas network for monocular depth estimation and FlowNet2 network for optical flow estimation. We refer to our paper for the optimization details. Let's go over a few results obtained using our methods now. We captured a variety of scenes using different cameras exhibiting distortions. We introduced multiple real objects such as animal figurines, rainbow balls, etc. in the scenes. We also create and place digital replicas of these real objects alongside them for fair comparison. The effectiveness of our results are best appreciated by observing video feeds. We can see that our method helps in simulating the correct distortion effects on the virtual objects, making the virtual objects indistinguishable from real ones. When compared to a naive compositing approach without any distortion effects, the result is striking and clearly shows how modeling such distortions correctly can enhance the realism of augmented scenes. We show a real-time demo of a scene deployed on MetaQuest 3 HMD, which exhibit the distortions model from the captured pass-through frames. The demo runs at 40 to 45 FPS while showcasing the distortion effects. Please see the supplemental video for more such captures. We compare with prior works of Okumura et al. And Mandel et al. In the scene, the virtual tiger is placed on the marker, which is used by Okumura et al., while ours do not use the same. All other animal figurines are real to demonstrate how the blur looks in real. We also compared to an extension of Okumura et al. By using their markers, but recovering parameters used by our model. Our method is able to synthesize very similar looking blur as compared to real figurines without needing the marker. Comparing to Mandel et al., their method is able to synthesize defocus blur, but they lack the directional nature of motion blur synthesis. In a small user study, we compared the different methods with ours. We provided the user with 2 tasks. In identification task, we asked the user if they can perceive a virtual object in the scene and report the failure rate. Ours was perceived as the hardest to distinguish between virtual and real objects. In the consistency task, we provided the users with 8-second video clips and asked if the distortions over the virtual figurines was consistent with the background. Ours was perceived as the most consistent among all methods. We have rigorously tested our system with multiple validation experiments on both real and synthetic data. The code and datasets are provided on our project webpage. In summary, we propose a new way of thinking on how to model camera distortions in the wild without requiring any explicit calibration target or controlled capture conditions. Our experiments show the viability of our approach and help us achieve superior performance compared to prior works. In future, we would like to extend our method to other distortion effects as well as improve the overall efficiency of our pipeline. Thank you for your attention.